Every large application starts as a monolith. This is not a bad thing. A monolith is an application where all functionality lives in a single deployable unit. Your user management, product catalog, payment processing, notification system, search engine, all in one Node.js process. You run tests, build it, deploy it, scale it as a single unit. The monolith has real advantages that are easy to overlook in the rush to microservices. Development is simple: change code, run the app, see the result. Deployment is simple: build one artifact, deploy one thing. Debugging is simple: errors have a single call stack that crosses all the functionality you need to trace. Transactions are simple: a database call in one function and a database call in another function can participate in the same transaction because they share the same database connection. At small scale, 1 to 5 developers, manageable traffic monoliths are almost always the right architecture. The operational complexity of microservices is a tax that only pays off at a scale large enough to justify it. But monoliths have failure modes that become painful at scale. The most important is deployment coupling. If your user service and your payment service are both in the monolith, you can't deploy a payment service change without redeploying the user service. The payment team must coordinate with the user team. As team size grows and deployment frequency increases, this coordination overhead becomes a significant bottleneck. Teams spend more time waiting for deployment slots than writing code. There's also the resource scaling problem. Your image processing feature is CPU intensive. Your user authentication feature is lightweight. In a monolith, you can only scale them together. If image processing needs 30 instances, authentication also runs on 30 instances, wasteful. These are the pressures that push monoliths toward decomposition. The question is how far to go and when. The microservice architecture takes the scale problem and inverts it. Instead of one deployable unit, you have many, each responsible for a single business capability. In a microservice architecture, the user service manages users. The payment service manages payments. The notification service sends emails and push notifications. The product catalog service manages products. Each service has its own codebase, its own deployment pipeline, its own database, and its own team. Services communicate with each other over the network, typically via HTTP REST APIs or message queues. The fundamental unit is independent deployability. The payment team can deploy a new version of their service without telling anyone or coordinating with anyone else. The user service team deploys on Tuesday. The payment team deploys on Thursday. The notification team deploys twice a day. Everyone moves at their own pace. Independent scaling follows from independent deployment. The product catalog service is getting hammered by a marketing campaign, scale it to 50 instances. Authentication is light, keep it at 3. You match resource allocation to actual load, service by service. The book gives a concrete example that makes the architecture tangible. Imagine an e-commerce platform. A user browses products, product catalog service. Adds one to cart, cart service. Proceeds to checkout, order service. Pays, payment service. Receives a confirmation email, notification service. Behind the scenes, inventory is updated, inventory service. Each step is a different service. Each can be worked on, scaled, and deployed independently. The advantages are compelling at scale. The disadvantages are equally real. Distributed systems are hard. Network calls fail. Services go down. Data consistency across services is complex. These challenges are the reason you want to start as a monolith and decompose only when the pressure to decompose is real. When you have multiple microservices, they need to talk to each other. The patterns for how they communicate have profound implications for coupling, resilience, and scalability. The first pattern is the API proxy, also called an API gateway. A single entry point sits in front of all your microservices. External clients, your mobile app, your web frontend, your partners' integrations all talk to the gateway. The gateway routes requests to the appropriate service. It also handles cross-cutting concerns, authentication, rate limiting, request logging. The gateway is the facade that hides your internal service topology from the outside world. The second pattern is API orchestration. When a single client request requires data from multiple services, say, a user profile page that needs user data from the user service, recent orders from the order service, and account balance from the billing service, and orchestrator service coordinates the calls. It calls each service, waits for responses, aggregates the data, and returns a single response to the client. The client makes one call. The orchestrator makes 3. The third and most sophisticated pattern is message broker integration. Services communicate by publishing and consuming events through a message broker like RabbitMQ or Kafka. The payment service publishes a payment completed event. The notification service listens for that event and sends a confirmation email. The inventory service listens for the same event and decrements stock. Neither the notification service nor the inventory service has a direct dependency on the payment service, they're only coupled through the event contract. This asynchronous, event-driven approach is what makes truly decoupled microservices possible. But it introduces eventual consistency. The inventory might not be decrement until milliseconds after the payment completes. Whether that's acceptable depends on your business requirements. For most operations it is. For some, like reserving a unique resource, it requires careful design. After covering the theory, the book is honest about what microservices actually cost in practice, and this is where many architects who lived through a microservice migration earn their battle scars. Distributed systems are fundamentally harder than single-process systems. In a monolith, a function call is a function call, it either works or it doesn't. In a microservice architecture, every service call is a network call. Network calls fail for reasons that have nothing to do with your code: timeouts, DNS failures, connection refused, dropped packets. Every service-to-service call must handle failure gracefully, with timeouts, retries, and circuit breakers. Data consistency is the hardest problem. In a monolith, you can wrap two operations in a database transaction. Either both succeed or neither succeeds. In a microservice architecture, if the order service updates its database and then calls the payment service, and the payment service is down, you now have an order with no payment. Getting these two back into a consistent state requires complex patterns, sagas, distributed transactions with two-phase commit, or compensating transactions. Debugging and observability require completely different tooling. Tracing a request across 10 services requires distributed tracing, tools like Jaeger or Zipkin that track a request ID across all the services it touches and reassemble the complete trace. Log aggregation across services requires a centralized logging platform like the ELK stack. The book's summary captures the calculus clearly: microservices add significant operational complexity. That complexity pays off when teams are large enough that deployment coupling is a real bottleneck, when different services genuinely need different scaling profiles, and when organizational boundaries justify separate ownership. If none of those conditions apply, a well-structured monolith is usually the better engineering choice. The goal is always delivering value, not architecture for its own sake.